Hi there, welcome back. In today's video, we are diving into long short-term memory networks, or simply LSTM. You might have heard them before. These are special type of RNNs, recurrent neural networks, that can actually remember things for a long time. Sounds exciting, right? But why do we need them? In our last video, we talked about RNNs and how they work well for sequences. But there was a big problem. As the sequence gets longer, RNNs start to struggle with remembering important information. This is what we call the long-term dependency problem. The network either forgets past data too soon or ends up with the exploding or vanishing gradient problem during training. So here comes the LSTM to rescue. It was specifically designed to fix this issue. Let's see how they work. Imagine a typical RNN with its repeating modules. It's usually just a single 10H layer. Pretty simple, right? But LSTM architecture is different. Instead of having just one layer, LSTM has four layers working together in a unique way. Let's break down into step by step. The LSTM is like long chain for repeating modules. But inside each module, we have three main gates: the forget gates, the input gate, and the output gate. These gates help LSTM control the flow of information. They act like a traffic signal, deciding what information to keep, what to add, and what to throw away. First, we have forget gate. This layer decides what information from the previous cell state we should forget. It looks at the previous hidden state and the current input, combine them and pass them through the sigmoid layer. Sigmoid function outputs value between 0 and 1, where 1 means keep this information entirely, 0 means forget this information completely. So if the output is close to 0, it means the LSTM will forget that piece of information from the cell state. Next, we move on the input gate. Here we decide what new information we are going to store in the cell state. First, we have another sigmoid layer that decides which value to update. Then a 10H layer creates a vector of new candidate values that could potentially be added to the cell state. Together, these two steps help us figure out the new information to store. The sigmoid layer acts like a filter and the 10H layer provides the possible updates. Now it's time to update the cell state. This is where the LSTM really shines. We take the old state and multiply it by output of the forget gate, effectively forgetting the things we don't need. Then we add the result of the input gate's decision, which give us the new cell state. Finally, we need to decide what our LSTM is going to output for this time step. First, we pass the previous hidden state to the current input through another sigmoid layer. This layer decides which part of the cell state will make it to the output. Then we push the cell state through a 10H function to squeeze the value between -1 and +1. Multiply this filter cell state by the sigmoid output, giving us the final hidden state. And that's it. That's how LSTM works. By carefully controlling what information gets remembered and what gets forgotten at each step. This clever gating mechanism allows LSTM to handle long-term dependencies much better than simple RNN. There are many variants of LSTM like this, and this. So next time you hear about LSTMs being used for tasks like speech recognition, text generation, or even time series forecasting, you will know exactly why they are so effective. If you enjoyed this breakdown and want to learn more about neural networks, don't forget like and subscribe and hit that notification bell so you don't miss our next video. Thanks for watching. I will see you in the next one. Bye for now.